Doctor, can you hear me clearly?
نعم واضح والشاشة أيضا واضحة جدا.
Okay. So good afternoon, everyone. This is Omar Farooq, and for today, inshallah, I will be presenting my topic, which is entitled as dairy products. Now, moving on to the presentation outline, I will first give you a brief introduction about the dairy products. Then I will talk about how we handle the milk at the farm, what are the how we pre-cool it, how we store it before we send it to the plant. After that, we will talk about receiving and processing milk in the plant itself. What are the treatments, how we produce milk, how we distribute it, etc. And then finally, I will give you one example of butter making, one dairy product production. Okay, and what are the requirement cooling loads for producing such product? And finally, the conclusion. Now, starting off with the introduction. Now, what is dairy? Dairy is basically any product based on milk that came out of mammals. Okay, so coconut milk, for example, almond milk is not considered as dairy. We only consider dairy if the milk came from a mammal. Okay, then we can use this milk to produce various products like butter, cheese, various types of cheese, ice cream, and yogurts. Now, this flow chart over here illustrates the steps to produce any dairy product. Okay, in the first step, we handle the milk at the farm, where we first milk the mammals or the cow. Okay, after that, we pre-cool the milk, and finally, we store it in a tank. Pre-cooling here means any cooling actions that were done before the product reached the plant. Okay. In the plant, we call it cooling. Before we reach the plant, we call it pre-cooling. Okay. After that, we will transfer the milk in some stainless steel tanks until it reaches the processing plant. In the processing plant, we receive first the milk. Then we make some processing steps like separation, homogenization, pasteurization. I will talk about them later. Those treatments are done either to make the milk itself consumable, or to convert it to different kinds of dairy products like cheese, butter, whatever. Okay. After that, the final step is packaging and distribution. Now, in this presentation, I will mainly focus on the first and the third step because they contain a lot of cooling procedures and a lot of treatment, etc. The transferring and the packaging distribution, they don't contain a lot of information. But here you need to be introduced to those types of treatments because they are very important. Okay. So starting off with the first procedure, which is handling milk at the farm. Okay. Now, why we need to pre-cool milk in the farm? Obviously, because we don't want the number of bacteria and harmful microorganisms to propagate inside the milk and spoil it. Okay, so this figure over here illustrate the number of bacteria per milliliter of milk versus the times that the milk will stay directly after milking at various temperatures. Okay, so here at the relatively elevated temperatures, the milk will spoil fast. Okay, relatively. So the preferable temperature limit is between 15 and 4 degrees Celsius. Okay. Because as you can see here, we have sufficient time to store the milk and then to bring it to transfer it to the plant before the bacteria colonies start to propagate and spoil the milk. Okay, and even 4 is the optimum choice because as you can see here, the number of bacteria is almost steady. Now, to pre-cool the milk, we have two methods. The first method is to use coaxial tube heat exchanger. The coaxial tube heat exchanger is just like the double pipe heat exchanger, okay? But the only difference is that it has a spiral shape, okay? And you know this have two concentric tubes, one fluid flowing in the inner tube and one flowing in the annulus region between the two tubes. Okay, the second one is the plate and frame heat exchanger. Now, the plate and frame heat exchanger is the most commonly used type. Okay, like if you Google now, you will not find coaxial tube heat exchanger. I just found it by luck, so I put it here just for your reference. Okay. Now
Omar,
to
just one
remind,
point. Sorry,
yeah.
Just one point here. For the plate and frame heat exchanger, الملك نفسه يدخل في البليت هيت اكسشينجر ولا يبرد يعني ريفرجرنت او فلويد ثاني وهو يبرد الحليب؟
الحليب والفلويد الثاني بيدخلوا في البليت هيت اكسشينجر هيت انتراكشن كده.
حتى الحليب هو يدخل في البليت اند فريم هيت اكسشينجر.
ايوه بالضبط.
اوكي ثانك يو.
So this is just to refresh your mind how the plate and flame heat exchanger work. The hot fluid enters the system and then it flows alternately between the plates. The same apply to the cold fluid. It flows and alternately float between the different plates, and heat exchange occur between the plates. Okay. Now the plate and frame heat exchanger, we have two types. We have the single stage plate cooler and we have the double stage plate cooler. In the single stage plate cooler, we basically use mains water as a cooling medium, and it enters the plate heat exchanger and it cools the milk to around 15 degrees Celsius. Okay. Whereas in the double stage plate cooler, we use two cooling mediums. First, in the first stage, we use mains water, okay, to cool the fluid to some extent, to cool the milk to some extent. Then we use chilled water to cool it further to 4 degrees Celsius, which is the preferable temperature for storage, as I showed you earlier in the graph. Okay. After we cool the milk, we store it in a tank, okay, to conserve it until we transfer it to the plant. Some tanks are equipped with refrigeration system to maintain the desired temperature level of the fluid of the milk, and sometimes we don't use it.
Omar, sorry to interrupt you. هاي الانيميشن انت عملتهم ولا تحصلهم من الكومباني؟
لا من الكومباني. هاي الكومباني هي اكسشينجر LTD.
اوكي، هاي الكومباني هي يعني تنتج هيت اكسشينجر خاصه للحليب.
يب بالضبط.
اوكي ثانك يو.
Okay, now here I found some design considerations whenever we want. اتفضل.
الفرق ان السنجل ستيج ان الملك بيخش على التانك 15 degrees then it cools further صح؟
في الدبل ستيج ولا السنجل؟
لا في السنجل
مرة واحدة we use only one cooling medium, mains water, it cools to 15 degrees Celsius.
بعدين ال 15 بتخش على الريفريجريتد ميلك ستورج تانك 4 يعني في كولينج تاني بيحصل، لكن في الدبل ستيج هي بتخش التانك اوريدي 4 فما فيش further cooling صح؟
مرات في further cooling this is just to maintain the 4 because you know there is heat losses. So يعني we use sometimes a refrigeration system to maintain 4 degrees Celsius. It depends يعني on the time. If we want to transfer it very fast, maybe we don't need to use refrigeration because we'll transfer it directly. But if the storage is intended for longer periods, we maybe not use refrigeration because heat loss will occur.
Omar, I just have a quick question here. So for the single plate cooler and the double stage, now both of them are giving me the same output for Celsius?
No, the single stage give you 15 degrees Celsius. Double stage give you 4.
But here at the refrigeration of the single stage, it's the storage would be at 4. How?
Yeah, the storage at 4 because we use additional refrigeration system. Refrigerant will enter, recirculate around the tank, and then leaves. Okay, so now here I found some design considerations whenever we want to design an efficient single plate cooler. The milk should be cooled to within 5 degrees higher than the incoming water temperature. Like you can see here, the outlet temperature of the milk is 15, which is around 4 degrees higher than the inlet water temperature. Okay, indicating a good design. Okay, and to do so, we need to adjust the flow rate of the milk milk cooling water flow rate should be adjusted to about double the measured flow rate of the milk. Okay, and once we know the flow rate, we can decide the number of plates and for the system. Okay, now
sorry, from where you got this design consideration?
This one I found it in a PDF file. I don't know. I think it's an Indian company or something like this.
Okay, thank you.
Yeah, okay. After we pre-cool the milk, we then send it to the storing tanks where it will be conserved until we pick it and transfer it to the plant. Okay, so the tanks are made of stainless steel, and they may be of a vertical or horizontal arrangement. The tank capacity range from 0.8 up to 19 meter cubed. Okay, and according to the pasteurized milk ordinance, PMO, this is a set of regulations, okay, that regulate the production, the packaging, the distribution of milk for high quality milk. Okay, according to them, the temperature should not rise above 10 degrees Celsius. Okay, and also we need to the system is equipped with some mechanical agitation system. Mechanical agitation, like there is just a propeller here inside the tank. This propeller is attached to a shaft. The shaft is driven by a motor. Okay, and why we need mechanical agitation? Because we need to maintain a uniform temperature distribution inside the tank. Okay, and why we use stainless steel? Because stainless steel may not seem the optimal material for preserving the temperature, because it's conductive, but yet it's a hygiene material. Hygiene material, I mean that it's very easy to sanitize it because it's non-porous. So any harmful bacteria or any materials that are stuck in the surface of the inner surface of the tank, it will not infiltrate to the bulk of the tank. So we can easily sanitize just the surface. Other materials may be somehow porous, so any harmful bacteria will infiltrate to the bulk of the material, which will be difficult to sanitize it later. Also, it's oxidizing resistant, so no oxidization will be developed in the inner surface, which will impact the flavor of the milk or the composition or whatever. Now, moving on to the third part, which is receiving and storing milk in the plants. Once the milk reaches the plant, it is directly pumped into an ample storing tanks. Okay, those storing tanks, as you can see here in the figure, range in capacity from 4 up to 230 meter cubed. Okay, and why they have high capacity? Because generally milk is being received to the plants in a much faster way than the rate of processing and distribution. So we need a high storing facility. Okay, the indoor tanks should have a minimum insulation R value of 8, whereas outdoor tanks should have an R value of 12. R value here is the thermal resistance. Okay, if we have high thermal resistance, it means that it is more difficult for the heat to be gained by the milk, okay, from the surrounding. Now, those tanks are also sometimes equipped with a refrigeration system. If so, we use chilled water or we use water propylene glycol solution, a mixture. We mix the water with propylene glycol solution because we want to reduce the probability of freezing, because water freezes at 0, but propylene glycol freezes, I think, around -60. Okay, so by mixing the water with propylene glycol, we reduce the probability of freezing. Okay, and the cooling methods, we either use refrigerated jacket. Jacket is an annulus region, okay, annulus region in the tank, where the cooling medium will enter, recirculate, and then it will be drained after we cool the product. And some plant just pass the milk in a plate cooler before we pump it to the tank, just like the pre-cooling method, to cool it to 4.4 degrees Celsius or less. Okay, but this is not always the case. Refrigeration, if provided, we use those methods. Okay. Sometimes we only rely on the insulation of the tank to keep the milk at the desired temperature. Now, moving on to the first treatment process of the milk, which is milk separation. Now, here I will ask you a question. Does the milk that you drink contain the same fat content as the milk that came directly out of the cow? Of course, no, right? The milk that you drink is somehow diluted, right? مخفف يعني less fat content. But how we diluted it?
عمر ممكن أجاوبك؟ الملك اللي نشترى بس لونه أبيض، يعني مشترك مع الحليب اللون بس لونه أبيض.
لونه ابيض لسه فات.
بس هو مش حليب اصلا يعني، بس اسمه حليب. اسمه يعني شنو المشترك مع الحليب؟ هذا اللي نشربه الاسم واللون، والباقي محتوياته لا شيء.
نعم بالضبط، هو بيقول سكيم ميلك.
سكيم ميلك
يعني حتى الفول فات ميلك ما يعتبرش
ما في اي شيء، كل شيء مسحب من عنده. اسمه حليب، اسمه.
ما فيش فايدة يعني.
Actually we do the separation process because the milk that came out of the cow we call it whole milk. Then we separate it into a high fat content solution called the cream, and another solution called the skim milk. The skim milk contain low fat content, the cream contain high fat concentration. Now after we separate it, then we combine them again but with different proportions. Like if you want the final dairy product to have high fat content, you mix high proportions of cream, low proportions of skim milk, and vice versa. Okay, now the separation, how it is done on the plant, we use basically a device. This device receives the milk by a pump, but the pump needs to be a little bit gentle when it transfers the milk, because if it do harsh agitation in the milk, churning may occur. Churning يعني تكون زبدة, and if يعني زبدة تكونت في البump, it will be a trouble.
Okay.
Now this is just to show you the fat content of different dairy products: whole milk, low fat milk. This is the range of the milk fat. Okay, sour cream, heavy cream. Okay, now the separation process can be done naturally. We just have the whole milk. If you just milk the cow and let it sit for a while, okay, the fat globules, يعني كريات الفات, will float in the solution. This high fat content, we call it the cream, as I said. The lower part, or the part that will maintain, is the skim milk. Yes, skim milk also contains some fat, but it's like negligible compared to the cream. Okay, but in the plant, we don't rely on this natural separation. We don't just leave the milk and let it separate. No, we use a device called milk centrifugal separator. It basically works on the principle of centrifugal force. You have a bowl-shaped device that rotates with some angular speed. This angular speed will generate a centrifugal force that is 3,000 to 6,000 times greater than the gravitational force. The gravitational force is the one that drives the natural separation here. But this one, centrifugal force, is greater, which will speed up the process. Okay, because in the plant we need to make the process fast. We will not rely on natural separation, and then it will be very slow to produce the milk. Okay, so here the separator rotates. The cream will be pushed towards the center, and the skim milk will be pushed toward the periphery, and then we can separate them. Okay. Now, after separation, we have the homogenization step. Homogenization is basically a mechanical treatment where milk is passed through a very tiny orifice, as you can see here. This is the initial milk. It will be passed through a very tiny orifice. Okay. By doing so, an instant turbulent flow will be initiated, which will decrease the size of the fat globules. These are the fat globules. Okay. Why we need to do this? Because if we reduce the fat globules, they will not recombine again and float to the top layer of the solution. So to put it short, we just make homogenization because we don't need any further natural separation to occur, as I just showed you before. Plus, we want the milk to be homogeneous. If you test the milk, it should have a homogeneous taste. We don't need to test it, have some parts with high fat, some parts with low fat. Okay. And the turbulent flow, you know, the vortex and the eddies in the turbulent flow, right? Those are the ones which are responsible to shear the big fat globules into smaller fat globules. Okay. And as you can see here, the cold raw milk, after 1 hour, the fat globules will float. But if you make the homogenization, it will stay for there even during the storage. Okay. Now moving on to the most important milk treatment process, which is pasteurization. It is basically heating the milk up to a desired temperature, up to a certain temperature level, holding it at that temperature for some time, and then rapid cooling. Okay. The inventor of this process is the great chemist and microbiologist Louis Pasteur, sorry, in the 1765. And pasteurization can be defined as a heat treatment process that kills all the harmful bacteria and microorganisms, okay, that naturally exist in the milk to make it more safe and consumable for the humans. Okay, two important factors need to be controlled whenever we do pasteurization, which is the heating temperature and the time of pasteurization. Because if we heat it, let's say you heat it a lot, you heat it to a very elevated temperature and hold it for a very long time, okay, you will kill the harmful bacteria, but this may also adversely affect the milk flavor, the milk appearance, the milk natural nutritional value, okay? So the careful control of these parameters will result in a good pasteurization process. Now, when we talk about pasteurization, there are two most commonly used methods. The first one is called batch pasteurization or VAT pasteurization, or even low temperature, long time LT-LT pasteurization. The second one is called the continuous pasteurization or high temperature short time, HTST pasteurization. Now, what determines what method we use is the processing rate. If the processing rate is 2050 kilogram per second or higher, it is more feasible to use the continuous type. If it is less than this rate, then it is more economically justified to use the batch pasteurization. Now, starting off with the batch pasteurization, the product is heated in stainless steel tank to not less than 62.8 degrees Celsius. Okay, and then we hold it at that temperature for about half an hour, followed by cooling. Now, there are three main processes in batch pasteurization. The first process is heating. We either use steam or we use hot water to heat the product. I will show you after a couple of slides how the heating action is exactly done. After that, the holding. Now, one important thing during holding is that the milk product, the maximum temperature difference between the milk throughout the whole milk should not exceed 0.5 degrees Celsius. Okay, between any region, like in the tank, between any milk point and another milk point, there should be no temperature difference above 0.5 degrees Celsius. Therefore, we need adequate agitation during the holding period. Okay. After that, we have two-stage cooling. The first stage, we use plant water cooling. Okay. Then we use refrigerated water or propylene glycol to further cool the product to about 4.4 degrees Celsius or less within 1 hour. Now, this is the configuration of the tank. Here where we will introduce the milk in this big space. Okay. Now, the heating medium will enter to this annulus region, which is called the jacket. Okay, heating medium will enter to the jacket, and heat transfer will occur between the heating medium and the milk. Then we will drain the heating medium. After that, we will introduce the cooling medium, whatever chilled water or propylene glycol. Okay, the heating medium will, cooling medium will be introduced to the same jacket. Heat transfer will occur also, and then we drain the cooling medium. Now, these are some of the important calculations when we use batch pasteurization. First, we can estimate the heating load in the heating process, which is the volume of the milk in the tank multiplied by the density of the milk, heat capacity of the milk, the temperature difference between the pasteurization temperature and the initial milk temperature. Now, once we know the heating load, we can estimate what's the quantity, the mass of steam or the mass of water required to do this heating job, okay, which is just the heating load divided by the enthalpy difference if you use steam, or heating load divided by also the enthalpy difference, Cp water, T initial of the water minus T final of the water if you use just water. Okay. Now, also, we have this equation number 4. We equate the rate of heat transfer through the tank by the instantaneous rate of heat of the milk. Okay. This in case we don't have any heat losses. Okay, U is nothing but the overall heat transfer coefficient, which is 1 over HI, which is HI, the milk side convective heat transfer coefficient. HO is the jacket side convective heat transfer coefficient, and K is the thermal conductivity of the vat or the tank. Okay, once we equate those two, we have a simple differential equation. We can separate the time variable to the left side, and you can separate the temperature variable to the right hand side. Okay, integrate both sides, you will end up with the heating time, or what we call it as the come-up time. It's a very important factor that needs to be predicted, which is Vm rho m CPM divided by UA ln TH is the heating medium temperature minus the initial milk temperature divided by TH minus T pasteurization temperature. Okay, the heating time is an important factor because we rely on the heating time, and then we have the holding time, and then we have the cooling time. All those factors are important for efficient pasteurization process. Okay, because if we let's say we heat it very rapidly, okay, this let's say we heat it very slowly, this might kill the harmful bacteria. In addition, it may adversely affect the milk. And if we heat it very slowly, vice versa. Okay, so we need to efficiently control this parameter. Similarly, for the cooling process, we have the T cooling, or what we call it the come down time. We can also estimate it this way.
So this come up time is the pasteurization process or not?
لا, come up time is heating time. We have we have heating. This is the temperature versus time. This is the come up time, and then we have holding time, and then we have cooling. This is the come down time, and this is the come up time.
اوكي بس انا قصدي الباسترايزيشن بروسيس اللي في الاول هي مش الكم اب تايم.
Pasteurization, all this process, the whole this process. Heating, holding, and cooling.
اوكي.
Remember, heating, holding, and rapid chilling or rapid cooling.
اوكي تمام.
Yeah. Now this is the system of batch or LT pasteurization. As you can see here we rely on a boiler which will produce hot water. Hot water will be introduced to the tank where it will heat the milk. Then we drain it. Then we introduce cooling water or whatever cooling medium to cool the milk, and then we will drain it also. Okay, this is the raw milk inlet, and this is the pasteurized milk outlet. Now moving on to the second one, which is the continuous or high temperature short time. In this pasteurization process, the milk is heated to at least 71.7 degrees Celsius, and then it's and then we hold it at that temperature for about 15 seconds only. In the batch pasteurization, we held it for half an hour. Here we only hold it for 15 seconds. It's a much faster process. Okay, the main components of this system is the plate heat exchanger, okay, where we heat and cool the milk. We have a balance tank where we store the milk, okay, and then pump it to the heat exchanger. We have the milk pump, okay. We have a holding tube where we hold the milk for the required holding period after heating, and we have a flow diversion valve. I will explain it later. Okay, the capacity of high temperature short time pasteurization range from 13 grams per second up to 13 kilograms per second, and the product should be cooled to at least 4.4 degrees Celsius or even lower to compensate for the heat gain that may occur during the packaging process. Now this is the continuous HT-ST system. First, milk here is introduced to the balance tank, then it will be pumped, okay, to the regeneration section. This is a plate and flame heat exchanger. Here we have cooling section, we have regeneration section, and then we have a heating section. First, it will be introduced to the regeneration section where it will be heated, okay. Then we pump it again to the heating section, okay, where we will complete the heating process. Then we pass it to the holding tube. Then the holding tube will, after that, will be passed again to the regeneration where it will be now cooled slightly. Then to the cooling section where it will be finally cooled, okay, and then we have the pasteurized product. Here we have something called the flow diversion valve after the holding tube. If the milk was not pasteurized well, we have a minimum set temperature here. If it was not pasteurized well, we return it back to the constant level tank or the milk balance tank to repeat the process. But if it was pasteurized well, we allow it to pass through the regeneration and then to the cooling, and then we have the final product. Now the plate and frame heat exchanger, we have the three main sections as I explained. We have heating, we have regeneration, we have cooling. The source of heating is either hot water or steam, and the source of cooling is either chilled water or propylene glycol. Okay. Now when we want to size this system, we need to make sure that the heating section, the temperature of the heating fluid entering the heating section should be not more than 1 to 3 degrees Celsius higher than the outlet temperature of the product. Okay, this is the outlet temperature of the product here, and this is the inlet temperature of the heating medium. It should be no more than 1 to 3 degrees higher than the outlet temperature of the product here. Okay, this is when we want to size the heating section. Whereas when we want to size the cooling section, it's usually sized such that the temperature of the pasteurized product, which is here at P8, okay, is about 2 to 3 degrees Celsius higher than the entering temperature of chilled water, which is here at C1. Okay, and finally, the regeneration section is sized such that it provides 80 to 90% regeneration. What do I mean by 80% regeneration? It means that 80% of the heating job is done by the regeneration, 20% is done by the heating section. And what's 80%, for example, regeneration in cooling? Meaning that 80% of the cooling is done by the regeneration, the other 20% is done by cooling. So it's an energy efficient way to pasteurize the milk. Okay, it reduces the requirement of heating and cooling by using the regeneration. Now these are some of the relevant calculations. Here, when we can estimate the number of plates by dividing the milk volume by the density, by the specific heat. This is what was this? The rise or drop in the milk temperature, okay, and by the U LMTD, log mean temperature difference, and by the area of the cross-sectional area of the plate, okay. And U here is nothing but 1/1 of the hot fluid. E plate divided by K of the plate. E is the thickness of the plate. K is the thermal conductivity. 1/H cold, the convective from the cold fluid side. We have also, this is the fouling factors if we have any. Okay, and then we can also estimate the regeneration by dividing the heat exchange in the regeneration section by the total required heating or cooling load. Okay. And by this, we can reduce the heating and the cooling requirements. So we have the actual heating load, which is the original heating load multiplied by 1 minus the regeneration efficiency. Also applies to the actual cooling load. And then we can divide this actual heating load and cooling load by CPH delta TH, which is the hot medium, and CPC delta TC of the cooling medium, to get what's the required flow rate of the heating medium and the cooling medium in the pasteurization process. Now moving on to the next part, which is the holding tube, where we hold the milk at a specific temperature for a certain time. Okay, ideally in the holding tube, we prefer to have a plug flow. Okay, because it will ensure a uniform holding time. Plug flow is a uniform flow. Here the velocity profile is uniform. Okay, because if you have plug flow, the holding time will be uniform. Like every fluid particle, when it once it enter and once it's leave, it will be holded for the same time uniformly. But this is actually not always the case. We in practice we commonly encounter laminar and turbulent flow. Okay, Reynolds number more than 4,000 is for turbulent flow, and Reynolds number for 2,100 is for laminar flow. And the holding tube should be designed such that the fastest moving particle receives the minimum allowable holding time. Like for example, here the maximum velocity is here. This it should be designed such that the particle here receives the minimum allowable holding time. And if this particle receives the minimum holding time, of course the other particles will stay for a longer time in holding tube. And by this, we can make sure that all the particles receive the minimum allowable holding time. Now moving on to the flow diversion valve, it is a device placed at the outlet of the holding tube. It is controlled by a temperature recorder controller to divert the flow back whenever it was not pasteurized well, or the product is below the minimum set pasteurization temperature, which is 72. 72 is slightly above the pasteurization temperature. It was, if you remember, it was 71.7. Here we just set it as 72 as a precautionary. Okay, we set it as 72. If the temperature is below, we divert it back to the balance tank where it will be pasteurized again. If it's higher, then we allow it to pass through the cooling section. Okay, there are two acting forces in the flow diversion valve. We have the spring force, and then we have also an air force. The imbalance between those two forces will decide the location of this valve. Okay, if it's pasteurized well, it will pass here. If it's not, it will pass here down. Now let's move to the final thing here, which is butter making, one type of the dairy products. Butter is made of the heavy part of the milk, which is the cream. Okay, the cream is pumped into a churner. Here, remember when I said for you the pump should be a little bit gentle to not cause butter. Now here we want the pump to drive the cream into a churner where it will be harshly agitated until we form a butter. Okay, the cream actually is separated into a butter, and the liquid part that will remain.
Sorry, Omar, to interrupt you. Do you have information what is the type of the pump that we use it for pumping the cream?
No, I didn't look at it.
Because I asked always the students in quiz one, what is the type of the pump we use it to pump the butter? It's diaphragm. It's a positive displacement diaphragm pump. So it's not centrifugal because it's difficult to pump butter with centrifugal, because when you pump it, it becomes thicker.
Yeah, exactly.
Okay, thank you. Sorry to interrupt.
Yeah, no problem. Thank you for the addition. Okay, then we we can separate the cream into a butter and a buttermilk. Okay, butter is generally stored at a temperature of 18 degrees Celsius. Okay, and the butter should be well protected and to prevent absorption of odors. Okay, because the butter easily absorbs odors from the atmosphere, so we need to make it well protected from that. Okay, here I will show you a video how we make a butter. Yeah.
Smoother, it's got more flavor.
So how is it made? Well, it starts with raw milk, which is shipped in from a farm in Middle Georgia.
They have to process the raw milk, they pasteurize it, they separate it, and we get the high fat version. Then we take the heavy cream, put it into the vat, and pump it in, and then that's where we begin the culturing process.
Culturing or fermentation, that's where bacteria is added to sour the cream. It sits and cools for roughly 24 hours, and timing is key. Any longer than that will cause it to become cheese. Once the fermentation is done, the cream is pumped into a churner, and that's where the magic happens.
The cream will bash up against the baffles. So all those little molecules, fat molecules that are in this heavy cream, they have a membrane around it, and it bursts. The butter and the liquid separate. So the butter and the butter fat and the buttermilk separate from each other. This is, real buttermilk. People, drank whatever in the 1800s. This is the real thing. This is not sour milk.
The buttermilk is drained from the churner and placed in gallon containers ready for sale.
The first thing we do is we grab the gallon and then we just put inside. If you are really good with it, you won't make a mess like me.
Oh, and then she puts more pressure on you, right? Okay. There it is. Gallon of butter away. Thank you so much.
Yep.
See, painless. Now back to the butter.
He's going to start what we call the washing process, where we push all of the whey out.
This is done by adding cold water, churning again, and draining. After 2 or 3 cycles, this is what you're left with. Pure butter. After testing, it's shaped, packaged, and shipped out. And that's how it's made. Yeah, now you're looking at something.
Okay, so this is how butter is made. Now we will move on to
There, that's about a good 85.
Yeah, okay. Now we will move on how to, some estimation of the refrigeration load. Okay, we have 2 refrigeration load. First is we need to size the ice builder. Okay, ice builder is the one that will make the icy water for the cooling purposes. Okay, and the next one is the storing facility refrigeration load. Okay, now here we have an example. Determine the product refrigeration load for a plant manufacturing butter from 6,000 kilogram of 30% fat cream, okay, per day. Now the first thing, if the cream is separated in the plant, it must be cooled from 32, the separating temperature, to 4 degrees Celsius. Okay, now how can we estimate the cooling load for this one? We will divide the cream mass by the temperature change by the heat capacity of the cream, divided by this one is the enthalpy of fusion of ice, because you use an icy water for this purpose. Okay, so this is the first cooling load. Then after pasteurization, the temperature of the cream is reduced by approximately 38 degrees with city water, then down to 4 degrees with refrigeration. Now this one with the city water, we don't care about it. This is a water coming from a plant or a water plant or whatever. We want to estimate for the next stage, which is up to 4. In this one, we use the icy water coming from the ice builder. Okay, so this one, we cool it from 38 to 4. 3.56 is as I said, the heat capacity of the cream divided by the enthalpy of fusion. We like assume that icy water will cool it and then it will fuse. Okay, so we use the enthalpy of fusion. So this is the second cooling load. And after churning is the process that I just show in the video, the agitation or the rotation process where we convert the cream into butter. The 15-degree butter wash water, you remember he washed it with an icy water. Okay, he flashed some icy water. So this icy water will drop in the temperature from the icy water is usually cooled from 15 to 7 to do this purpose, to splash it on the butter. Okay, so to do so, this is the additional refrigeration load. 15 minus 7, 4.187 is the heat capacity of water. So this is an additional refrigeration load. If we add them all, we have 4,560. And we may consider 100% losses to add. We will end up with this refrigeration load. This is if we want to size the ice builder. Okay. Now, if we want to size the storing room, we have here approximately 2,250 kilogram of butter is obtained. How it's obtained from the 600 kilogram cream. The cream has 30% fat content, right? So in total, we have 1,800 kilogram of fat. And let's say if the butter contain approximately 80% of fat. So if we divided this one by 80%, we will have 2,250 kilogram of butter can be obtained from this 6,000 kilogram of cream. Okay, this butter temperature going into a refrigerated room is usually about 70 degrees Celsius and then must be cooled to 4 degrees. Okay, so 17 minus 4, this is the mass of the butter, and this is the heat capacity of the butter. We have this amount of refrigeration. We also, the metal container of the butter itself, we also reduce its temperature because the total system is butter inside the metal container. Okay, the metal container, let's say it's in the initial, it is in the room temperature. We also reduce it up to 4 temperature, just like the butter. We have this amount of refrigeration. Then after 24 hours, the butter is removed from the cooler to cut it and wrap it in those paper container that when you buy the butter, it's wrapped in some like paper or aluminum. I don't know, this container. Okay. During this process, the butter temperature rise to approximately 13 degrees Celsius, which constitute another product load in the cooling when it goes back for the refrigeration. Okay, so this additional, because the temperature rose to 13, we need to bring it back to 4. So we have 13 minus 4. This is an additional refrigeration load. And also during this step, we will take the butter from the metal container in the paper container that we know. Okay. We also reduce the temperature of the metal container, let's say from room temperature to also 4, which is the butter final temperature. We have this amount of load. If we add them all, we have this amount of refrigeration load of the storing capacity in 1 day. So to conclude, the dairy products production was illustrated. I showed you how we handle the milk at the farm, what are the pre-cooling steps, how then we store it in the tanks. I also discussed how we receive and store milk in the planets, what are the treatments, what is pasteurization, homogenization, and different kind of treatments whenever we want to produce dairy products. Okay, the milk treatments, as I said. Finally, I showed you one example of dairy product production, which is butter, and what is the necessary refrigeration loads that need to be estimated whenever we want to produce it and store it. So these are just set of references that you need to, if you want to visit them, feel free to visit them. And thank you for listening. And if you have any queries, you can feel free to ask me.
Thank you very much, Omar. I really appreciate it. I can say this is the most important or most informative presentation during this session. It's really very nice. I liked very, very much. And I got a lot of useful information. And this is what I want. In fact, I want also you to focus on estimating some loads, some calculations. So you explain the steps and the procedures, and you explain the system, and also you did some estimations. So I would be very thankful if you share with me the slides, and also you share with me the references, because especially the references used to get these examples.
Yeah, of course.
Really, thank you very much, Omar. Shabab, do you have any question, please? Okay.
That's excellent.
Okay. The second point, please. The IRU unit من الجامعة send you survey. And last class I asked you, please.